Let's dive right in. In the 3.2 release of Blender, the ability to create and use named variables returned to geometry nodes. The data stored in variables can be positions, color information, or general data. On display here, we have Brady Johnston's molecular nodes, which add tons of information to the node trees for making custom selections. In this video, we're going to look at setting up and using variables in a simplified case for placing atoms on graphene. This will be a slightly more advanced tutorial, so if you're new to Geonodes, you might want to check out the Getting Started video linked in the description. As always, there will be timestamps below for those who want to skip ahead. Because we are getting a bit more advanced, we'll start with a discussion of indices. Every mesh object in Blender will have verts that store position data and can also be used for other information. Curves, in contrast, will have control points, which serve a similar function. It can be helpful to see the indices on your mesh, so I'm going to use an index visualizer made available by Mohammed Riaz. You can get this on Gumroad for free, I've linked it in the description. To use the file yourself, simply open a new Blender file, append from the directory where you've stored the actual downloaded file, so you can see it's right here, and then we're going to come to node tree, and we're going to append the specific node tree that says append this. Then, using a very simple plane to demonstrate, I will simply grab this, come to the Geometry Nodes workspace, create a new Geonodes network, and with Shift-A, I'll come to Group, and I will append the index viewer, placing it between the input and the output. And if I come to a top view in the viewport, zoom in, and let's go ahead and bring the scale up just a little bit, you can now see this is identifying the 0, 1, 2, and 3 indices, which, if we move over to the Geometry Nodes spreadsheet, you can see these each have an associated position. And this is the index value down here. What we want is to assign a custom variable to each point, and we're going to use that ultimately to control the atom placement in a graphene sheet. In the simplest form, all I'm going to do is select my index visualizer, hold down Alt first, and then drag it out of the way just to preserve this connection. And with Shift-A, I'll come to Attribute, Store, Named Attribute, and place this between. You can give your variable any name you want. I'm just going to call mine Variable. And then you can assign any value for each point. You'll notice it's appeared in the spreadsheet, and right now it has a default value of 0. And I could assign this a very specific value. I could do it on the basis of the index, I could do it on the basis of the position, or some other form of imported data. For now, we're going to transfer over to the graphene file, and we're going to use custom variables to control atom placement. The finished graphene file and a similar version for nanotubes that I will briefly showcase at the end of this video have been added to the free assets I have on Gumroad, and those are linked in the description. Both are also compatible with the asset library. To start, we're going to walk through how I've made a sheet of graphene with selections that limit it to a square or rectangle. If you want to skip ahead to the explanation of custom variables, this is a good time to do so. If we zoom in on our graphene generator nodes, we can come to the first part, which is graphene creation. Very simply here, if we go ahead and hit Alt and Shift and left click, we can see in wireframe mode the individual components of our graphene. We start with a simple mesh grid, we subdivide this and put this control out to the user so they can control the density essentially of the grid. Then we use a triangulate node set to fixed alternate to create the triangles and a dual mesh node that creates these lovely hexagons. From there, we're very simply going to rotate 45 degrees in the Z direction, minus 45 degrees in the Z direction, and then scale by 0.6 in the Y axis to create this lovely little diamond of graphene. Here, we're going to use a mask node to create the rectangle or square selection. And the simple idea here is that we're going to compare every point to the absolute maximum of a primitive cube. Now, our graphene is only in 2D, but this would technically work in 3D within limits. And very, very simply, we're going to compare the X and Y positions, find out if they are greater than after we've subtracted to a range that is defined by the user. If either of these is true, then we will delete those faces. And it's very important that we delete the faces rather than the points. By deleting the faces, we lose any stray verts that might stick around and cause us problems later on for atom placement. If we go ahead and visualize this, you can see we have this nice rectangular selection, and we can adjust this through the aspect ratio X and Y. Even though they are both set to 1, it's clearly not an actual rectangle of 1, so you'd have to adjust accordingly to get something a little bit more even, but the idea is that you have sliding controls over the graphene sheet without having the forced diamond shape. Finally, it's important to note that the option to scale our grid is put in place after we delete the excess faces. That way, changing the scale doesn't change the comparison against the initial cube, and so we'll always make our selection correctly initially, and then if we want our lattice to be bigger, we can simply control it here using the scale. We now have our adjustable graphene sheet. We can change the size, the aspect ratio, the grid density, and you can see all of these on display quite readily right here. So the number of units, we can simply change the density, and we can also make this larger or smaller to suit our needs. If we wanted to, we could also move along the tree a little bit, and you can see there's a series of animation nodes, and these, if placed right here between this node and this node, will actually allow you to manipulate this and have it animate through noise, distortion, waves, and all kinds of other options. But what about atom placement? Let's say we want to place atoms on only the bottom half of our sheet, or in every other location for something like boron nitride. One way to do this could be with the index, the 0, 1, 2, 3, 4, 5. We'll use a simplified example to examine what happens here. In a simplified mesh grid, we can do many of the same things we did before. So if we wanted to, we could go through the fixed alternate triangulate and then a dual mesh to create the hexagons. However, if we want to place atoms on, let's say, every other point, as we would have in boron nitride, we could do this quite easily with the index of our original grid. So for just a moment, we're going to ignore our instance on points, which we're placing the atoms, and we're going to add in an extra append index node so we can see what's going on. And if we look at the index viewer, then we can see very clearly 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, you get the idea. They're all going up very nicely, and we have this very easy to work with alternating selections. So we'll go ahead, we'll delete that. And using this with a little bit of math, we can look at the index of each position, take the remainder of 2, spitting out the even and odd values, and then we can place atoms on every other point. So for the first selection, we're just going to say, for every point where this is even, we're going to use that, and then we're going to pass that through a Boolean not to choose every other point. We'll instance a simple UV sphere on those points, adjusting the scale, just so you can see the difference between the two, and then we go ahead and we see the geometry. Unfortunately, this falls apart very quickly for our graphene example. After we triangulate and use dual mesh, you can see the index values have changed. They are still increasing somewhat sensibly, but how they are placed in space means that we now have rows of odd or even instead of rows where we can easily choose between one and another. And what that means is if I wanted to place an atom on every other point, 2, 18, 6, 22, 10, etc. are all even points. So I'm not going to be able to use that selection to place nitrogen here, boron here, nitrogen here, you get the idea. And this is quickly going to get out of hand for larger sheets. If we return to our procedural graphene, we can see that what we want is to create selections for all the positions that are in a row or column. We want to assign that row or column a value that is corresponding to the index, and that's going to be stored in our custom variable. To get this information and convert it into clean numbers, we're going to use the position of each point in space. So even if, let's say, this was index 29 and this down here was index 76, they're both going to have the same value because they, along with these other points, are all in the same column. Similarly, every point up here on this top row are going to have the same point, and the next one down will have a different point. And the math that we're going to use is going to create a nice linear scale here, where each of these is an integer moving away from the 0 point at the center line. It's worth noting two things right now. One is that we're going to set up these variables early in the node tree, before we move any positions. For instance, these are the nodes that are storing the custom variable, and they are placed before any animation happens, and also before any other nodes that might manipulate the actual positions of our grid. The variable is going to store the position as it stands at this point in the network. If I were to manipulate those positions before storing the variable, it would cause problems. After the variable is created, I can move the sheet freely without worrying. The math that we're going to use is going to account for the scale, and so we don't have to worry about that aspect. The other thing worth noting at an advanced level is that position of other objects can be used to store information. In Brady Johnston's superb molecular nodes, multiple copies of the same structure are imported. Each has the same number and order of indices. But the structures use their extra X, Y, and Z values to store information about the types of amino acids, which protein chain an atom belongs to, color data, and so much more. It's a very clever technique that he details more in his series, which I've linked below. Ultimately, what we'd like to be able to do in the longer term is to import all of that data directly into something like a CSV for a single object, and that will be the subject of a future video as it develops. For now, the key concept is to understand that we are using the X and Y positions of every single point to create custom row and column selections for our graphene, and we're storing those for later use in the variables YMap and XMap. Let's briefly look at the indices and see why this is necessary. So we're going to go ahead, come to group, we'll add in the index viewer right here, and we'll connect right after we've done our initial graphene transformation. We'll then go ahead, create a join node here, and we'll bring the scale down just so we can kind of see what we're working with. So if I zoom in, you can see every single point here has an index, but all of these are kind of disjointed. Sometimes it looks like they'd give nice, even, odd numbers. So 84, 85, 86, perfect. But now I have 86, 88, 0, and those are all going to be even together, so I couldn't use these for an alternating selection. The two nodes that are kind of worth mentioning here are 0 and 1, because regardless of how I change the number of divisions, 0 and 1 are pretty much always going to be at this position, and they're always going to be right in the center. And that is very useful for the math that I'm going to use to create the custom selections. So without any further ado, let's actually take a look at those selections. We'll start with the generate Y positions. If I go ahead and open this node, you can see I'm taking the position at every point. So grab this individual vert and look at its X and Y position. I'm going to take just the Y positions using a separate XYZ node, and then I'm going to look for the field, namely the Y value, at the index of just 0. So 0 was right here. I want just this value. And then I'm going to divide every single Y position at every index by whatever the value is at 0. And the reason for that is, if we bring our grid density down, you can see if this is position 0, then by dividing by itself, I'm going to get 1. Every value in this row is going to give 1. Every value in the next row will give 2, 3, 4. And then below, -1, -2, -3, and -4. And this is going to continue to work regardless of the number of units. And it's also going to work regardless of how we scale these values for our crop. The key thing here is that there is a round right at the end, and that's just because some of the way that Blender handles float division doesn't always add up cleanly, so we're going to round to nice, even integers. And if we go ahead and come out of this, we can Control-Shift, left-click, connect the geometry here, and then we can see essentially that that is what is happening. So at a specific index, let's say 5, we have a value of 1. We also have a value of 1 at 0, and so we know that 0 and 5 must be along the same row. That is very useful for our selection. If at any point you are trying to recreate something like this and you can't find the specific node in the large menu, just go to search and then search for the one you want. So field at index, for instance. Returning to our index visualized version, we're going to briefly look at some of the math for X and why this is important. One of the things you'll notice with Y is that it didn't care about the scale or the number of units because it was always looking at that offset. The X values are determined similarly but a little different. We're going to grab the position, look at the X, but this time we're looking at the field at both the 0 and 1 position. So right here and right here. We add those two values together, divide by 2, and that's going to give us the kind of average distance from the center point. So right about here. Now, for every single X value, we'll divide by that value right there, and we'll use a ceiling function. So if it's above that or below it, it'll essentially allow us to sort all of the X values into either being in this specific column or this specific column, because the offsets are not the same. So the distance from 0 to 5 is not the same as it is from, let's say, 1 to 0. And so this math will essentially correct for all of that. And again, we get the same idea where everything here will be an offset of 0. This will be 1, 2, 3, 4, 5, 6. You get the idea. And I'll just go negative in the other direction. All told, this is going to give us our series of custom selections. And ultimately, the take-home message of this tutorial is that variables are extremely useful for making custom selections. In many cases, they may require a bit of math and some attention to the indices and other available data, such as positions. It's also possible to not fully rely on variables at all. now that we have our custom variables ymap and xmap, we can use the information stored in these, which you can now see in the spreadsheet, later on for controlling atom placement. If we move over here to see where the actual graphene is being generated, this bottom segment right here is just using a mesh to curve and then setting the radius of a curved circle to create our actual graphene lattice by itself. This is connected to a selection that allows us to put atoms on every other place, and the toggles are actually found in the modifier panel. So if I wanted to, I could change atom 1 and atom 2 size. Let's do that right now. And I could also change the materials to make it something more like boron nitride. If I want everything to be the same, then I simply set it all to the same value, and this would be roughly the graphene look that we have. I'm going to use an example of storing, or actually using, our named attributes and doing something a little bit more simplistic. So the boron nitride selection is right here. You can see it uses two named attributes. If we open this up, there's a series of Boolean logic that goes through, essentially spits out all the sites. What we're going to do instead is grab the network from this point here. We're actually going to hide the atoms using this toggle right there. And very simply, I'm going to drag off of there, create an instance on points, drag from here, create a UV sphere, and then I'm going to scale this down quite considerably, 0.01 to start. We'll use Alt, Shift, and left click to visualize that. And these are all our graphene positions. For the sake of argument, we'll also join that up with the actual output right here. So we'll go ahead, grab this and this, just so we can actually see the lines. Now, what I'd like to do is be able to use this selection with our named variables to decide which of these should have atoms and which shouldn't. And I'm going to do that in a gradient going from X to Y. So very simply, I'm going to grab a input, come to attribute, named attribute, and then I'm going to grab my named attribute, namely the point xmap. I'm going to pass this through a math node, and I'm going to actually pull this out and say compare. So it's not a math node, we're actually going to do a compare. Are we going to say, is this value here less than or equal to whatever this value is? And if that is true, it will place the atoms. So we go ahead, we connect this. You can see every value on this side is less than or equal, and so that is true, which means that the xmap is actually flipped. But if we go ahead and we change this by just dragging, you can see that we can now populate all of these across. And so this has some interesting tools for animation. The other thing that's worth noting is the values that we actually have to go up to. So in this case, if we wanted to go across, we'll use a smaller example. Let's bring this value down to just say 1. So we could do this in integer increments actually, because this actually is using integers. Connect that again. And then we can say very simply, everything at 0 is populated. Here's 1, here's 2, 3, and 4, which means it's going from 4 to -4. So if we go ahead and drop down to -3, then the only atoms that will have points are right here. So that is the essence of how we're going to actually use the X and Y map values for custom selections. And now that we have these very clear delineated columns and rows, we can do whatever we want. But there's one extra benefit that's absolutely worth mentioning. We're going to bring this back up, get rid of our extra atoms. And now we're going to come to the shading workspace. And you can see here, this is the same graphene sheet we had before. But now I've added an attribute node, mapped the range from a -8 to a maximum of 8. So this should be actually the full range. We're using Y in this case. So 1, 2, 3, 4, 5, 6, 7, 8. And so we want to go from the absolute minimum value to the maximum value and reroute that from 0 to 1 to create a nice gradient. Using the Y map, all I have to do to actually access this information is use input, attribute, and just type in the name. So Y map. In this case, it doesn't actually appear. You have to type it in, but all I do is connect the factor here. And then all I would have to do is connect this color. You can see I actually have a nice gradient going all the way across. What this means is that you can transfer attribute data into shader nodes using named attributes. And this is very easy. Beforehand, you had to capture attributes, transfer them out, create extra attributes for the object specifically, and this allows you to do it in shader nodes very straightforwardly. So there are some fantastic examples floating around the internet of how this has been applied to other things. BBN19, I believe, has created essentially roads using this, and you just simply draw a curve and it creates what looks like a highway. So this is a very nice trick that you can really gain some extra value if you want to do custom shading as well. Again, the take-home message here is that we are using the variables and they're useful for a variety of selections. To wrap up, I'm quickly going to showcase the Nanotube nodes. These have a number of interesting features because they are based on curves instead of on a mesh object. I can control where the tube starts from or stops, and I can use this to animate growth. I also have control over the radius, and you'll notice that when I bring this out, the aspect ratio changes. That's because all of the controls for the number of hexagons around, the segments controls, and then also the controls for the resolution, the number of hexagons along the length, are separately exposed for the end user to decide how they want this to look. You could update it so that they grow easily, but I wanted this to be something that the final user could decide for themselves. And you can see that this looks squished now that I've brought it back. So we'll change this down to about here, and that looks good for the time being. As before, we have the ability to create a carbon nanotube or a boron nitride nanotube, where every other point is a different atom. And unlike previously with our graphene, where that was a sort of grid selection, this is a little bit more animated. So you can see that I've got carbon in atom 1 and nitrogen in atom 2. Nitrogen is blue, and when I drag this slider, it actually starts to populate from one end all the way to the other. And so this is a way to animate along the length. I can also separately control the atom sizes and of course the bond sizes as well. As I mentioned before, this is available for free. The one nice thing that you can get out of this, because it's based on curves, is that if I want to, I could of course duplicate this, place it wherever I wanted, and then I could animate them all together, growing or shrinking. However, what I could also do is select this object, tab into edit mode, and then I could simply draw a new carbon nanotube using this selection right here. So I'll draw. And now, any of these will all obey the same animation, same tube, same radius. The only one that doesn't work is the boron nitride slider, where it will affect the tubes in the order that they were created. So if I tab back, you can see that one of these will turn completely black first, and then the rest will follow. So this one will be the last one that will turn blue. Hold down Shift and drag. So you can see this one's already blue. This one's starting to get blue at the end, but the other two are already blue. So that is the only control that doesn't work, where you would have to make separate tubes. Well, one of the nice things about all this is that, again, they will all animate kind of at the same time and finish at the same time, regardless of whether or not they're different lengths. If you do have problems with the drawing, one thing that is worth checking is hitting N for the side panel, coming to Tools, and just making sure that your maximum radius is set to a reasonable value. In this case, I have it set to 0.1 because that works. If I were to set this to something like 1, for instance, and then try and draw, I'm going to get a very distorted tube because it's using the same segments and resolution, even though it needs 1 for something that is much smaller. So what you want is to make sure that the maximum radius stays at a reasonable value, and then you can kind of draw tubes to your heart's content. Again, the point that I'd like to drive home here with the nanotubes is that you can often get away with just index-based math, and you don't have to rely on variables. The perovskite nodes also use entirely index-based math. For now, I'll call it quits here, with a reminder that you can download and use the Graphene, Nanotube, or perovskite nodes for free from Gumroad for any purpose, along with a variety of other assets. And to wrap, hopefully this tutorial has given you the tools to make your own custom selections for these nodes or your own. If you do make something and you want to share your creation, please check out our community Discord, linked below, or tag me on Twitter @CGFigures. A massive thank you to my Patreon supporters who help make these more in-depth tutorials possible, along with the release of all of the assets. If you'd like to support the creation of more tutorials or assets, there's a link in the description. If you found this useful, consider subscribing and sharing this with your friends and colleagues. And with that, thanks for coming out, and as always, you have yourselves a great old day.